Hello and welcome to part 2 of my series on neural networks. Right now I'm in my robe and it's pretty comfortable. I'm going to discuss the mathematical structure of the neural network. It consists of nodes, layers, and equations. It's all this really cool stuff, and let's get started. Alright, so here's the general structure of a neural network. You have the input layer, which is a vector of inputs. They are represented by these red circles, and each of these red circles represents a neuron or node. In this presentation, we will call these red circles or white circles or green circles, any circles, neurons. So you have the input layer, and it's connected to what is called the hidden layer. The input layer is connected to the first hidden layer. So you can see that each and every input neuron is connected to each and every neuron in the first hidden layer, as you can see here. Then you have hidden layers. You have the first hidden layer is connected to the second hidden layer, which is connected to the third hidden layer, etc., until you reach the last hidden layer. Then the last hidden layer is going to be connected to the output layer. And just like before, the connections are between each and every neuron. So between hidden layers, you have one neuron connected to all the other neurons. Then until you reach the output, in which you have the second to last layer, which is the last hidden layer connected to all neurons in the output layer. So yeah, that's the general structure. So now let's zoom in on the connection between the input layer and a hidden layer node. So what we have here is we have the inputs x1, we have x2 and x3, and so on, x4, x5, whatever. And we have what are called weights. So each and every connection has a weight associated with it. For example, we have the weight between the input neuron 1 in the input layer and the neuron I in the first hidden layer, which is represented by 1I. And that 1 in the superscript over here, that represents the layer that that I is in. So this 1 represents the layer that this I, the second connection, is in. And each and every neuron in this first hidden layer has what is called a bias. That is the B sub I. And they also have something called a Z sub I, which is the weighted sum. Z sub I is the weighted sum of the inputs and weights multiplied together plus the bias. And then you also have what is called an activation function. You can think of it like how the neuron is going to activate in response to these to Zi, in response to that signal. And it's going to be a function of Zi, or Zi1 if you want to be more technical, because that's the layer right there that corresponds to the first layer. Well, should we call the input layer 0? And we call this layer over here that this neuron is in layer 1. Then you have layer 2, layer 3, layer 4, and so on, until you get to the output layer, which is layer, I don't know, capital M, we could say. And we can represent this in where we have z sub I superscript 1, where we have this summation. We can represent this summation as in matrix form. And that's going to be a dot product between W transpose and X vector plus the bias. The bias you can think of it as like something like a threshold at which maybe if it's lower than a threshold, the neuron will activate. Maybe if it's higher than a threshold, then it will activate. Yeah, so it gives it a threshold. And yeah, that's the mathematical equation that is equivalent to this over here. Then you have your activation function. We'll worry about that in a bit. Let's now connect the input layer nodes to all first hidden layer nodes. So we're going to connect each and every red neuron to each and every white neuron in the first hidden layer. And so now we have a matrix of weights in which we still have the dot product, except now we're extending it in the vertical direction. So then we have Z1, Z2, Z3, all the way up to Z capital N sub 1. So that's going to be all of the weights in the first hidden layer because there are N1 neurons in the first hidden layer. And then we have, the weights, for example, this weight over here, that's the weights that corresponds to the connection between the weights associated with the connection between the second neuron in the input layer and the second neuron in the first hidden layer. And this represents over here the weight associated with the connection between the last, or the N sub 0, that's how many neurons are in the input layer. So that's going to be the connection between the last neuron in the input layer and the second neuron in the first hidden layer. As you can tell, because of this superscript 1, it's connecting the previous layer to the next layer being the first layer, layer 0 to layer 1. And then you're multiplying that by the X vector, your input vector, plus your biases. Each and every first hidden layer neuron is going to have an associated bias all the way up to bias N sub 1. So you could represent this as a vector z superscript 1 is equal to W superscript 1 transpose, because remember we transposed it, multiplied by X plus B, which is the matrix of the vector of biases associated with the first layer, or the first hidden layer. Then we have the activation function. Therefore, the activation function, we're going to say that that's going to be a vector it's going to be equal to a vector function. That's a function of the vector z superscript 1. Alright, so now let's zoom in on the connection between one of the hidden layers, we'll say hidden layer J, and a node within the next hidden layer, we'll say J plus 1. So all of these neurons in the Jth layer are connected to this neuron in the J plus 1th layer. and this is the ith neuron in the J plus 1th layer. And you can see over here we have the weight connecting neuron 1 in the jth layer and neuron I in the J plus 1th layer, for example. And then we have the bias B sub I J plus 1 of this neuron over here. And we have the Z sub I, which is, that summation over here. So each and every one of these neurons in the previous layer, layer J, they all have activation functions which they shoot over to this neuron, and we're going to represent that as a summation of those activation functions in the jth layer times the weights. They're going to be weighted, and we're going to add a bias term, that bias term of the ith neuron in the J plus 1th layer, and that's going to equal to our Zi J plus 1, our signal. And so then we have the response of our neuron as described by this activation function A sub I J plus 1. And so it's going to be the response to that signal over here. And yeah. And so once again, we can represent this in the Z sub I signal of the J plus 1th layer in matrix form, or vector form, or the dot product. You have the W transpose W sub I J plus 1 transpose times activation functions of the jth layer, right? Because the activation functions are going to be weighted. Then you're going to add that bias term, of course, for the ith neuron, the J plus 1th layer. That's going to be equal to your signal, the signal that the neuron receives, and in turn, it's going to be activated in accordance with this activation function. So let's now connect the hidden layer J nodes to all of the hidden layer J plus 1 nodes. So this is the jth layer, that's the J plus 1th layer, and we're going to connect each and every one of these nodes to each and every one of the other nodes. And if we do this, we get to a matrix of weights multiplied by the activation functions plus the biases. In our weight matrix, for example, we have this over here. That is the weight associated with the connection between the n sub jth, or the last neuron in the jth layer, because there are n sub j neurons in the jth layer, and the second neuron in the J plus 1th layer. And all of these activation values are from the jth layer, all the way up to n sub j, because there are n sub j neurons in the jth layer. And then once again, you're going to have the activation functions. They're going to be like a vector. Because you made this into a vector, you're going to make this into a vector as well. Let's zoom in on the connection between the last hidden layer and an output node. So we're going to call the last layer layer M, and we're going to call the second to last layer, therefore, layer M minus 1. The second to last layer is the last layer of the hidden layers, and the last layer is the output layer. So once again, we have A1, A2, A3 activations of these neurons in the last hidden layer, and these activations are going to send a signal to the ith neuron in the output layer, and we're going to get a weighted sum of those activations in accordance with the weights, plus the bias term over here that corresponds with this neuron, the ith neuron in the output layer, and that is going to be the signal that this neuron experiences, and then y sub I, that is going to be the activation of this neuron, which is the output. So y sub I is going to be a function, specifically the function for the ith neuron in the output layer, m, a function of z sub I superscript m. So we can once again represent everything, the connection between the last hidden layer and the ith neuron in the output layer. We can represent the equations in the signal that is sent to the output neuron in matrix form, and we can express the activation over here. So let's now connect the last hidden layer nodes to all output layer nodes. And we can once again display everything in matrix form. You have the weights, you have the activation functions of the previous layer, and you have the biases, you have the signal that's sent to the output neurons, and then you have the activation of the output neurons. So here's a summary of all of the equations. When you have an input layer to the hidden layer, you have these equations. When you have a hidden layer to a hidden layer, you have these equations. And when you have the connection between a hidden layer to the output layer, you have these equations. So these are just the equations describing the connections between the layers. Alright, thank you for watching, and I hope you learned a little bit about the mathematical structure of neural networks. I will retreat to my room so I can sleep, and have a good night, or morning, or afternoon, whatever time it is. For me, it's night. So, good night.